This is college algebra, which is Math 1111. In Unit 1, we will be discussing functions and linear functions. The sections we're going to cover include sets, linear equations in one variable, linear inequalities in one variable, linear equations in two variables, linear systems, and relations versus functions. The first section we're going to cover is sets. We're going to start off with the definition. What is a set? A set is a collection of objects whose contents can be clearly determined. Objects in the set are referred to as elements, and sets must be well defined. That is, the contents can be clearly determined. So for example, the letters in the English alphabet, we know that is A, B, C, D, E, all the way up to Z. So we know for sure what is contained in there. It doesn't have to be a finite number of things. We could just say whole numbers. And there's an infinite number of them, but we know what's in the set. Whereas something that would not be a set by this definition could be the 5 best songs of all time. Because everyone's going to have a different set of 5 best songs. Going from person to person, that set could change. Or sorry, that group could change. So by this mathematical definition, the 5 best songs of all time would not be a set. There are a few different ways we can represent sets. We could have a word description. So for example, set n is the set of whole numbers greater than 0 and less than or equal to 9. We could list them using the roster method, which is where we list each of the elements. So we have set n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. And then there's set builder notation. This is read as n is equal to the set of x such that x is an integer greater than 0 and less than or equal to 9. So this little picture down here is telling you what each of the things mean. So when we have these curly brackets, that stands for the set of. The next thing is going to be our variable, which we read as all x. The vertical line stands for such that, and then we read the mathematical state. In this case, x is greater than 0. So we would read this as the set of all x such that x is greater than 0. Now that we know what a set is, we're going to talk about different sets. First up, we have the universal set. The universal set is a general set that contains all the elements under discussion. So this is going to be our idea of everything that could be. So we could take our universal set to be the students in class right now, in this class right now. Or we could say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's our universal set. Now from our universal set, we can take subsets or groups within that group. So mathematically, our definition of a subset is set A is a subset of set B expressed as A is a subset of B. So this kind of looks like a less than or equal to sign, but instead of the less than, it's kind of C-shaped. If every element in set A is also an element in set B. So for example, if we let set A be equal to the set containing 1, 3, 5, and 7, and set B be the set that contains 1, 3, 5, 7, 9, 11, then we can say that A is a subset of B, because 1, 3, 5, and 7 are all elements within B. So B is the larger group, and A is the group that we picked from B. Thinking back to the example on the last slide, we had our universal set as all the students in this class right now. One subset we could take from that would be the students in this class right now currently wearing glasses. So from that group of students in class, we're taking only those wearing glasses. Now the students in class wearing glasses are clearly part of the students in this class. So that's this idea of subset, taking part of the whole. Now the empty set is probably the weirdest idea when it comes to sets. The empty set is going to be the set that contains no elements. It's also called the null set, and it's represented in one of two ways. We can either use the curly brackets and putting nothing between them, or we can use a circle with a line through it. Those both mean the empty set, so the set that contains no elements. So for example, the set of all numbers less than 4 and greater than 10. Well, there aren't any numbers that are both less than 4 and greater than 10. That doesn't happen. So that would be the empty set. Or the set of x such that x is a person taller than 12 feet. There aren't any people like that. So that set would be empty. Thus we have the empty set, also called the null set. So now that we have some of our vocabulary about sets, we're going to start doing things with sets. We're going to start with a complement. The complement of set A, symbolized by A with an apostrophe after it, or A prime, it is the set of all elements in the universal set that are not in set A. This idea can be expressed in set builder notation as A prime, or the complement of A, is equal to the set of X such that X is an element of U, the universal set, and X is not an element of A. There are other notations for the complement of a set. Sometimes it will be the set name with C written as a superscript, or the set name with a bar over it. In this class, we'll be looking at it with an apostrophe notation, but these two are also fairly common. So we're going to start looking at some examples. First up, if the universal set is U is equal to the set of X such that X is a positive integer less than 12, and set N is the set that contains 2, 3, 5, 6, 7, 9, what is N prime, or the complement of N? I'm going to start by writing out U, the universal set, in roster notation so that I can see what all is contained within U. So U is going to be all the positive integers less than 12. So that would contain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Because it said less than 12, so we don't get to include 12. If we are looking for the complement of N, that means we are looking for the elements that are in here, but are not in set N. So what I'm going to do is I'm going to go to my universal set and cross off everything that is in my set N. So that'd be 2, 3, 5, 6, 7, and 9. What's left is going to be my N prime. So the complement of N is going to be equal to the set that contains 1, 4, 8, 10, and 11. You can always check your work by comparing the set and its complement. If you put these two sets together, you should get back to the universal set. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's my universal set. So that will be the complement. If the universal set is U, is the set that contains A, E, I, O, U, and set S contains A, O, and U, what is the complement of S? I don't want A, O, or U, So that means the complement of S will be the set that contains E and I. Next up, we have the intersection. Now, when I hear intersection, I think of where two roads meet. So this area right in the middle. That's the intersection to me. Well, if this horizontal road is Main Street and the vertical road is First Street, well then, if I'm in the intersection in here, am I on First Street or am I on Main Street? Well, I'm on both. I'm on First Street and I'm on Main Street. So what intersection means is and. Mathematically, the intersection of sets A and B, written A upside down U shape, B, is the set of elements common to both set A and set B. This definition can be expressed in set builder notation as follows. A intersect B is equal to the set of X such that X is an element of A and X is an element of B. So what you need to take from this is that intersection means and. So let's take a look at an example. If n is equal to the set that contains 1, 2, 3, 4, 5, 6, 7, 8, 9, and m is the set that contains 0, 2, 4, 6, 8, and 10, what is n intersect m? To be in the intersection, we have to be in both n and m. So I'm going to compare the sets and figure out what do they have in common. Not 0, not 1, but 2 they have in common. Not 3, but 4 they have in common. Not 5, but 6 they have in common. Not 7, but 8 they have in common. Not 9, not 10. So this will be my intersection. N intersect M is equal to the set that contains 2, 4, 6, and 8. Now we want to know what is N intersect the empty set or the null set. Well, we see that N contains 1, 2, 3, 4, 5, 6, 7, 8, 9. Our empty set doesn't have any elements. So we're trying to figure out what is in our set N and in our empty set. What do they have in common? Well, they don't have anything in common. There are no elements that are in both N and our empty set. So the intersection between N and our empty set is the empty set, which again we can write either as the circle with a slash through it or as the empty curly brackets. One more operation on sets that we're going to look at is called the union. The union of sets A and B, written as A, U symbol, B, is the set of elements that are members of set A or of set B or of both sets. This definition can be expressed in set builder notation as A union B is equal to the set of X such that X is an element of A or X is an element of B. So what you need to take from this is that union means or. So we're taking the two sets and putting them together to create one larger set. We're going to bring back the same sets, N and M. So set N contains 1, 2, 3, 4, 5, 6, 7, 8, 9. Set M contains 0, 2, 4, 6, 8, and 10. We want to find N union M. So what we're going to do is we are going to list everything from N and everything from M. So N union M will be the set that contains 1, 2, 3, 4, 5, 6, 7, 8, 9. Those all come from N. And then we want to tack on everything from M, which would be 0, 2, 4, 6, 8, and 10. There are two things I want to point out here that are really going to be helpful. When it comes to curly brackets, meaning we're talking about sets, we don't have to list repeats. So for example, 2 appears on my list twice. I don't have to write it twice. 4 appears twice. I don't have to write it twice. 6 and 8, same boat. I don't have to write them twice. The other thing is that when you're in curly brackets talking about sets, order does not matter. So you could write these in any order you want to. I just really prefer to put them in numerical order. That's fine. If you want to leave them in the order that they're in, that's fine too. But if I want to put them in numerical order, I'm going to write them as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's everything that is either in N or in M or in both, but listed only once. If we want to find N union the empty set, then I'll kind of do like I did last time. N union the empty set is equal to, I'll start by listing everything in N. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I need to add to the list anything in the empty set. Well, there isn't anything in the empty set, so I have everything. You'll notice that this is just set N again. So now that we have complements, intersections, and unions, let's see if we can put them all together. If set U is our universal set and it contains 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, N and M are what they have been. And now we're going to introduce set P, which contains 1 and 2. First up, we want to find N union M prime, so the complement of N union M. So similar to how we have the order of operations, we're going to follow that same idea when it comes to set operations, which means we need to start in the parentheses. So in parentheses, I have N union M. Well, I just found that. So if I list out what is an N union M, that was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now that I know what N union M is, now I can find the complement of it. Now remember, the complement is everything in your universal set, which in this case are the integers between and including 0 and 11, but not in the set that you're taking the complement of. So if I go down the list and cross out what is in N union M, I'd cross out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That leaves only 11. So N union M complement is going to be the single element 11. In the next one, we want to know what is N complement intersect M complement. So this time I don't have parentheses, so I'm going to do what looks like exponents to me, because that's what seems to make sense in the order of operations. So first up is N complement. So I need the things in the universal set that are not in set n. So that'll be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are all in n, so that leaves 10 and 11. So I have my n complement. Now I want m complement. That's going to be everything in my universal set that is not in m. So that will be 1, 3, 5, 7, 9, and 11. Now that I have n complement and m complement, I want to find the intersection. Remember, intersection is what they have in common. So what is common between two lists is just 11. That's the only element that they have in common. So our answer is just the element 11. You might think that it's interesting that we got the same answer for both of these. It's actually a property that is called De Morgan's Law. We won't be looking at De Morgan's Law in this class, but if you continue on in mathematics, that'll be a really useful thing in the future. Next up, we want to know what is M union the empty set. So we start by listing everything in M. 0, 2, 4, 6, 8, 10. And then include on the list, because union means put them all together, anything in the empty set. But there isn't anything in the empty set. It's empty. So I'm not adding anything to the list, which means I'm just getting set M back. Finally, I want to know what is N intersect M union P. Again, thinking in terms of order of operations, I need to do what is in parentheses first. That is N intersect M. So looking at N and M, what they have in common is 2, 4, 6, and 8. We found that before on the first slide on intersections. It's what they have in common. But now that I have the set N intersect M, I want to take this and union it with set P. So that means list everything in this set and add to it the elements of P, which is 1 and 2. So I need to add 1 and 2 to this list that I already have. But 2 is already on the list. I don't have to write it twice. So that means when I union them, I will have 1, 2, 4, 6, and 8. Again, when it comes to curly brackets, when we're dealing with sets, order doesn't matter. So if you wrote the one last or put them in some random order, that's totally okay. As long as you have curly brackets on the outside and the numbers 1, 2, 4, 6, and 8, your answer is good. We're going to take this idea of sets and apply them to intervals. So all of the numbers within a range. Now this is something that we will use forever and forever in college algebra and beyond. So this is going to be something that is so super crazy important. What we're going to do is we're going to start with an inequality, and we are going to see how to write it in set builder notation. We're going to see how to graph the inequality, and we're going to write it in interval notation. Starting with set builder notation, that's the one where we have the vertical line. I know that one's a little bit funky, but you'll see as we work through these why it can be useful. For most of these, set builders are going to be really easy. So our first inequality, we have 1 is less than or equal to x, which is less than or equal to 3. I would write it as the set of x such that, so opening curly bracket x, vertical line. Then I'm just going to copy the inequality. 1 is less than or equal to x, which is less than or equal to 3. That's it. Close your curly bracket. For negative 4 is less than x, which is less than 0. That's going to be the set of x such that negative 4 is less than x is less than 0. For x is greater than 5, we're looking at the set of x such that x is greater than 5, and that's it. For x is less than or equal to 1, we will have the set of x such that x is less than or equal to 1. Now we're getting into this idea of OR. The great thing about set builder notation is that we're allowed to use words. So we're going to look at the set of x such that, and just like the others, I'm going to copy this over. X is less than 1, or x is greater than or equal to 5. Same thing on the next one. We can use words in set builder notation. We're looking at the set of x such that 2 is less than x, which is less than or equal to 3, or x is greater than 10. This last one is all real numbers. So that's going to be almost anything you can think of. Negative 5, positive 1/2, negative 0.23896. All real numbers. The way we're going to write this one is a little bit weird. I'm going to write the set of x such that I want to include all real numbers. So I'm going to say x is a real number. So to kind of review what this set builder notation means is I'm going to take all x's. Use any variable here I want. It's not going to change anything. As long as a value is greater than or equal to 1 and less than or equal to 3, then it is going to be an x value that satisfies this inequality. If it satisfies the inequality, then it's part of my set. So that's how the set builder notation works. Now we're going to look at graphs. Now the space I have for graphs is not very big, so I'm going to use a separate sheet of paper. So first up we have 1, let's use a different marker. We have 1 is less than or equal to x, which is less than or equal to 3. So what I'm going to do is I'm going to create a number line. And on this number line, I have to remember that smaller numbers go to the left and bigger numbers go to the right. So when I write this, I need 1 to be to the left of 3. Those are the only two numbers I care about, 1 and 3. I am going to put circles on 1 and 3. What type of circle is going to depend on the inequality symbol. If I have a less than or equal to or a greater than or equal to sign, I'm going to use a closed circle. If I have a less than or a greater than sign, I'm going to use an open circle. So in this case, because they are both less than or equal to signs, I'm going to use closed circles. These closed circles mean that these values are included in the set. So x equals 1 satisfies this inequality. It's greater, the value 1 is greater than or equal to 1 and less than or equal to 3. But all the values between 1 and 3 also satisfy this inequality. So what I need to do is highlight those, and the way I usually do it is by trying to make it bolder. So what this is showing is that 1 is included, 3 is included, and all of the numbers in between. Let's do the next one. We have negative 4 is less than x is less than 0. On my number line, the two important numbers this time are -4 and 0. I made sure that -4 is to the left because it's smaller. This time, I don't have equal to as an option, so I need to use open circles on both of them. But the numbers between -4 and 0 do work, so I still need to shade the area in between them. So any number between, but not including -4 and 0 works in this case. Next up, we have x is greater than 5. So on my number line, it looks like I only have one important number, and that's 5. Since I don't have equal to, 5 needs an open circle. But all of my x's that satisfy this are greater than 5. Numbers greater than 5 are to the right, like 6, 7, 28.3. So I need a way to say all of these numbers forever. So I'm going to shade to the right. But I keep going forever. 89 billion satisfies us. So I'm also going to shade the arrow. So any number on the number line to the right of 5 satisfies that inequality. We're going to see something very similar for x is less than or equal to 1. So 1 is my important spot. I do have equal to as an option, so that's going to be a closed circle, meaning 1 works. But I need my x's to be less than or equal to 1. So I need to shade the numbers that are less than 1. That's going to be to the left. So I need to shade everything to the left, including the arrow, because I can go on forever. Now we're going to get to the ones that are a little bit trickier. X is less than 1, or x is greater than or equal to 5. So on my number line, I have my important numbers 1 and 5. We have an open circle on 1, it's just less than. We have a closed circle on 5 because it's greater than or equal to. Let's start with x is less than 1. To make x is less than 1 on the graph, we start at our open circle and go to the left. So I want to shade everything over here. Or x is greater than or equal to 5. So to do x is greater than or equal to 5, I shade to the right of 5. So we could be over here, or we could be over here. And you might ask yourself, why is this important? When would I use something like this? Think about tickets. Sometimes the tickets will be discounted for children and senior citizens, but adults are more expensive. So if your age is less than 13 or greater than or equal to 65, then you get the discounted price. If your age falls elsewhere, then you're going to have the full price. So it really does have an application. Even if you don't see the graph, we do see things like this. Next up, we have 2 is less than x is less than or equal to 3, or x is greater than 10. On my number line, we're going to have 2, 3, and 10. They don't have to be spaced out perfectly. I'm not going to have enough room to do 2, 3, and 10, so we're just going to fake it. I need an open circle on 2 because we don't have equal to. I need a closed circle on 3 because there is an equal to. And I need an open circle on 10 because there's not an equal to. Starting with my first inequality, we have x's between 2 and 3. So I need to shade the numbers between those. So that covers that part. Or x is greater than 10, so I need to shade to the right of 10. So we could be between 2 and 3, or we could be greater than 10. Finally, we have all real numbers. No, it doesn't seem like we have an important value here because there's not really one that's more important than the others. Just so I have a point of reference, I'm going to say 0, but it's just so I have something. I need to shade this entire line. So having 0 there, it doesn't really matter. I need the entire thing. It just makes me happy to have at least one number on there. We need everything. Now that we have the graphs, we're going to work on writing interval notation. And having a graph is going to make writing interval notation significantly easier. Interval notation is a way of writing an interval to where you don't need to include the variable. It's only going to tell us about the endpoints, and then anything in between we just assume is included. So first up, we have 1 is less than or equal to x is less than or equal to 3. In interval notation, we're just going to focus on the endpoints. So the numbers that we're looking at are between 1 and 3. So the endpoints are 1 and 3. Then we need to decide whether to use parentheses or square brackets on each side of this interval. Just like we had closed circles and open circles, we're going to follow the same rules. If we have a closed circle, we're going to use a square bracket on that side. And if we have an open circle, we're going to use parentheses. So in this first case, we had closed circles on both 1 and 3. We also had the equal to signs. So both of those point to using square brackets on both sides of our interval. So to write this inequality in interval notation, we have 1, 3 with square brackets on both sides. Next up, we had -4 to 0. So our endpoints are -4 and 0. This time we had open circles on both sides. Open circles mean we need to use parentheses. Next up, we have x is greater than 5. So on the left, our endpoint is 5, but I don't stop. I keep going forever in that positive direction. Well, if I keep going forever, I'm never going to hit a maximum number, but I am going towards this idea of infinity. I'm just going on forever, getting bigger and bigger and bigger. So we're going to say our other endpoint is infinity. But because we can't actually touch infinity, we cannot be equal to infinity, we're going to use parentheses. And then we'll also have parentheses on the 5 because that was an open circle. To kind of go along with this, anytime you use positive or negative infinity, and be using parentheses because we can never be equal to either positive or negative infinity. So if you're ever using one of those, then you're going to want to use parentheses. Next up, we have x is less than or equal to 1. So it looks like on the left side, since we're going forever to the left, that'll be our negative infinity. And on the right-hand side, we have 1. Because it's a negative infinity and we can't equal it, we'll have parentheses. On the right-hand side, we have a closed circle at 1, so that will be a square bracket. Now is a really good time to point out that when we're working in interval notation, we are going to want to make sure that we're always working from smallest to largest. Notice that the smaller number comes first, 1 then 3. It would be wrong if you wrote 3 then 1, because that doesn't make sense. We want to work from smallest to largest. Having a graph makes this really useful because you can see what's on the left and what's on the right. Next up, we have x is less than 1 or x is greater than or equal to 5. And I don't think I'm going to have room to write this one, so I'm just going to kind of come back to this. Here's our graph. So it looks like here we have negative infinity up to 1. and one would have parentheses because it's an open circle. Over here, we would have 5 to infinity, and 5 would have a bracket because it's a closed circle. Now this idea of OR takes us back to sets. We had a word that meant OR. That was union. So I want to put a union between those. So this is how I write this inequality in interval notation. Negative infinity to 1, union 5 to infinity. Next up, I will have the interval from 2 to 3, parentheses on 2 because it's an open circle, bracket on 3 because it's a closed circle, or, so union, 10 to infinity. For this last one, all real numbers, I don't really have left and right endpoints. I can have anything, so we will write this as negative infinity to positive infinity. So now that we have this interval notation, and it's not going anywhere, we will use interval notation forever. We're going to use it to help us with something a little bit more complex. First up, we want to graph the set P is equal to the set of x such that x is less than 2, or x is greater than or equal to 7, and write it in interval notation. So let's start by graphing it. Our two important spots are going to be 2 and 7. We have an open circle on 2 because we don't have equals. We have a closed circle on 7 because we do have equals. X is less than 2 means go to the left. So we want all of these. Or x is greater than or equal to 7, so greater than is going to be to the right of 7. So now I want to write this in interval notation. So that will be negative infinity up to 2, parentheses because the 2 has an open circle, or, so union, 7 with a bracket because it's a closed circle up to infinity. This next one's a little bit weird. It says to graph the set S, which is the set of x such that x is greater than negative 3 and x is less than or equal to 2, and write it in interval notation. So we need a negative 3 and we need a 2. We need an open circle on the negative 3. We need a closed circle on the positive 2. We need to be greater than negative 3, which would be from negative 3 that way. And we need to be less than or equal to 2, which would be from the 2 that way. If I need to be in both of those at the same time, that means I'm between them. The numbers between negative 3 and positive 2 are the ones that satisfy this. It's a little weird because it's not written the way we would think. We would normally write this inequality as negative 3 is less than x is less than or equal to 2, but that way is completely okay too. And having it written like that is going to help us moving forward because it's going to make things a little bit easier. So to write this in interval notation, we have a left endpoint of negative 3 with parenthesis, a right endpoint of 2 with a square bracket. So these interval notations really are sets. They're sets of numbers. We just want to take them and perform some operations on them. So like we had complement, intersection, and union before, those are sticking around. So given two sets, find the union and graph it. So I'm going to start by graphing these two sets. So on my number line, I'm going to need a negative 2, a positive 6, a a positive 3, and a positive 11. Make sure they're in order from smallest to largest, because if you don't, then things are going to get really, really wonky. I will graph set A in blue. And I'm going to go above the number line so I don't mess up my markers. So -2 would have an open circle, 6 would have a closed circle, and I want the numbers in between. I'm going to graph set B in red. That's going to have an open circle at 3 and a closed circle at 11, and I want the numbers in between. Now I'm trying to find the union of these two sets. Union means or. So I need to be in set A, or in set B, or in both. So as long as I'm in one or the other, or both, that's going to be included in this set. So I need to include all of the numbers that are blue, or red, or both. So that starts at -2 with an open circle, which would be parentheses. And I'm in blue, I'm in blue, I'm in blue. At 3, I have an open circle in red, but we're still in blue because we have the line through there. So we're okay. We're in both, that's okay. We're in red. We stop being in red after 11. So 11 is going to be our right endpoint, and because it's a closed circle, we will get a square bracket. So we would write this as -2 to 11. Any number between -2 and 11, including 11, is in this union. Next up, we're going to look at the intersection. So we have the same sets A and B. So we have a -2, a +3, a +6, and a +11. I did A in blue. So open circle at -2, closed circle at 6. And then we did B in red. Open circle at 3, closed circle at 11, stuff in between. This time we're finding the intersection. Intersection means and, so I need to be in both of them. So I need to be in both blue and red. So wherever blue and red overlap, that's going to be between 3 and 6. This time, 3 is not in red because open circle. If it's not in red, then it's not in both blue and red. So we're going to use parentheses. Whereas 6 has a closed circle, and the line indicates a closed circle. So 6 is in both. So we will have a bracket on the 6. Next up, we're given two sets. We want to find the intersection. So same thing as last time. I'm going to set up my number line. It looks like we need a 6 and an 11. Set A is -infinity up to 6. So 6 will have a closed circle, and we want to go to -infinity. Set B will have an open circle on 11 and go to infinity. And we want to find the intersection. So where are we in both blue and red? Where do they overlap? They don't. This word disjoint at the end of the title is saying that these two intervals don't overlap at all. So the intersection, A intersect B, does not exist. There isn't an intersection. All right, this last one, A has two intervals union together, and then we have B. So let's see if we can create a graph for this one. So we're going to need a 6, a 12, a -2, and a +23. So first up we have A, which is -infinity to 6. or 12 to positive infinity. So that's going to be our blue set A. And then set B is -2 to positive 23, which is red, with open circles on both and stuff in between. Now we are looking for the intersection, so we need to be in both blue and red. So where do they overlap? Between -2 and +6. It looks like we have an open circle at -2 for red, so that'll be parentheses, but a closed circle on 6, so bracket. But then we overlap again from 12 to 23, so we'll have union 12 to 23. We have an open circle for blue at 12, so parentheses. We have an open circle at 23 for red, so also parentheses. So what you really need to take out of this section is that intervals are sets, and we can do our operations on them. Intersection means and. Union means or. And we are going to be using interval notation the rest of this class, so make sure you are comfortable with interval notation.